Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. In this lecture, we are going to discuss how to train logistic regression with the softmax output. Now, you might be asking, wasn't logistic regression the prerequisite to this course? And the answer is yes. But importantly, we must recognize that we didn't cover all of logistic regression. In particular, the one topic we didn't cover was how to do multi-class classification, which was a topic I saved for this course. Now, because of this, you might have mistakenly thought that logistic regression is only for binary classification, and to have multi-class classification, you should use neural networks, but that is not the case. In fact, you can mix and match different types of models and different types of tasks, depending on how complex you want your model to be and what your task is. I created this table to help summarize each of these combinations. By the way, this table is like a cross product between these two different sets. The first set is the type of model, either a linear model or a nonlinear neural network. That goes in the horizontal axis. The second set is the type of task, either regression, binary classification, or multi-class classification. That goes on the vertical axis. The topics highlighted in red were covered in the prerequisites, while the topics highlighted in green are covered in this course. So as you can see, anything that has to do with neural networks is part of this course. But we also have one linear model which is part of this course, and that's multi-class logistic regression. What I want you to remember is that there's no mathematical reason for this choice. It's rather just a practical distinction. It's easier to learn about binary classification first, before you learn about multi-class classification. This particular lecture is going to be about training a multi-class logistic regression model. As you progress through this section, you'll understand why this makes sense. First, we're going to start with all the pieces we need to do this derivation. Our prediction is y equals the softmax of w transpose x. Remember that we are now using the convention that y represents the model output and t represents the target. So the objective will be the sum over n and the sum over k, t of nk times log of y of nk. If you recall, we said earlier that this is the negative log likelihood, and it is also the multi-class or categorical cross-entropy. As usual, our job is to minimize the loss L with respect to the weight matrix W. As a side note, since the negative sign is somewhat superfluous and all we'll end up doing is copying it over and over again, it's easiest just to drop it completely and work with an objective that we want to maximize rather than minimize. Of course, this is just the log likelihood of our model with respect to the data instead of the negative log likelihood. So what do we do? Well, we know that this problem doesn't have a closed form solution for W. If you're not convinced of this, you should try to solve for W and see how far you get. Our strategy then is going to be use gradient descent or gradient ascent. In order to do this, we have to find the gradient of J with respect to W. Then, once we have that, we can use our iterative gradient descent algorithm to move W in the direction of the gradient until it converges to the solution. The thing that's challenging about this is that we have a lot of functions of still more functions. In other words, the expression for J doesn't involve W directly. The expression for J depends on Y depends on A, and A depends on W. So how can we find the derivative of J with respect to W? The answer is the chain rule. Whenever you have a function of a function of a function and so on, you can use the chain rule to find the derivative. So for example, suppose we have J equals f of z, z equals g of y, and y equals h of x. Then the derivative of J with respect to x would be dj by dz times dz by dy times dy by dx. Similarly, we can apply the same logic to multi-class logistic regression. Of course, our next job is going to be to calculate these three derivatives on the right side. Now, if you only glance at this, it might seem pretty straightforward. But the funny thing about this equation is, the more you consider it, the more confusing it will get. Unfortunately for you, that's exactly what we're going to do. So the astute among you may wonder, why is there a k on the left, but we're summing over k prime on the right? Why do k and k prime both show up on the right? The way I like to remember this is that the summation index is a dummy variable. Remember that anything involving the summation index cannot exist outside the summation. So for example, if you have a dot product, the sum of xi times y of I, you are not allowed to bring any of the terms outside the sum because that doesn't make sense. Another way to think about this is in terms of programming. Unfortunately, you have to know some C++ or Java to understand this example, since it doesn't really apply to Python. So if you do, then great, and if you don't, then just ignore this example. We can see here just a simple for loop where we print each element of an array. When we're done, we try to print the value of I. Unfortunately, this doesn't work because the variable I does not exist outside the for loop. It's just a dummy variable that exists inside the for loop. Here's one final statement I want to make about dummy variables. It's important to remember that it doesn't matter what you call them. That's why they are called dummy variables. For example, notice that the two equations you see here are exactly the same. It doesn't matter if we call the dummy index I or j, because it's just a dummy index. The same goes for programming. These two for loops are equivalent. It doesn't matter what I call the dummy index, it will still print the same thing. So going back to our chain rule expression, the dummy index used for the summation is k prime. It cannot exist outside the summation. The k that we have on the left is not a dummy index, and it refers to the output index of the weight w. So I represents the input index and k represents the output index. Notice also that n is a dummy variable. It exists inside the summation, but it's not allowed to exist outside the summation. The most important derivative here, I think, is the middle derivative, d of y and k prime by d of a and k. This is, of course, because that's where the boundary is, where we switch from k prime to k. Now you might ask, why do we switch from k prime to k? Good question, and this is important. If you recall, y is just the softmax of a. So now you realize there's something non-trivial about this softmax function that we have to deal with. This is also, by the way, why you learn about binary logistic regression before you learn about multi-class logistic regression, which is quite a bit more difficult. It's easier to see if we draw a picture and use real numbers. Let's suppose we have three output activations, A1, A2, and A3. Then we have three corresponding output probabilities, Y1, Y2, and Y3. We can calculate these probabilities using the softmax function. From this, it's easy to see that Y1 depends not only on A1, but also A2 and A3. Similarly, Y2 depends on all of the A's, as does Y3. What this means is there are actually 9 different derivatives we need to consider. dy1 by dA1, dy1 by dA2, dy1 by dA3, and so on. Importantly, we can see that there are instances where the index for y is the same as the index for a, but there are also instances where the index for y is not the same as the index for a. In other words, it doesn't make sense to only consider dyk by dak. We also have to consider the instances where we have dyk prime by dak, where k prime is not equal to k. Now, what does this mean in terms of a neural network or logistic regression? Well, it simply means that the probability at one output node depends on the activations at other output nodes, and hence depends on the weights that go to the other output nodes. That makes sense because in order to get a probability in the first place, we have to divide by the sum of all the activations combined. Okay, so that's nice, but how does the math actually work out? Since this is the only non-trivial derivative, and we're already talking about it, let's do this one first. Personally, I like to apply the product rule, but you can also apply the division rule of calculus if you've memorized it. In other words, it's helpful to move the denominator to the top and just take it to the power of -1. Now again, you can see that we're using yet another dummy variable, this time j, because we don't want it to interfere with the variables outside the sum, which are k prime and k. Alright, so before we do anything, we have to first decide whether or not k prime is equal to k. Because if it is, then we have to differentiate the first term. If it's not, then the first term is constant with respect to k. For the purpose of this lecture, we'll first assume that k prime is not equal to k, so the first term is constant. So after differentiating, we get this. Remember that the derivative of the exponential is just itself. If you want to do this by hand on paper, you are most certainly encouraged to do so. One interesting thing about neural network derivatives is that they have convenient expressions in terms of the output variable rather than the input. So we can express y, which is a function of a, in terms of y instead of in terms of a. So if we reorganize the derivative a little bit, you can see that we can express it in terms of two softmaxes multiplied by each other. And this is just the negative of y of nk prime times y of nk. Next, let's consider the case where k prime is equal to k. In this scenario, we can just replace k prime with k since they are both the same. Now we can see that both terms depend on a and k, so we have to differentiate both and apply the product rule. Again, you are highly encouraged to do this yourself on paper if you don't see right away how we arrived at this answer. Remember that the derivative of the exponential is just itself. Just like before, we can conveniently express this in terms of y's. We can see that it's equal to y of nk minus y of nk squared, which is also equal to y of nk times 1 minus y of nk. Alright, so now we found these two expressions for the derivative of the softmax. Since we have to plug this back into our loss derivative, it would be nice if we could combine these into one expression. Now, you'll see that I've expressed the second derivative in a very particular way. In particular, I've put y of nk prime for the first instance of y, but I've used y of nk for the second instance of y. Of course, technically they both yield the same result because k prime is equal to k. However, this form is convenient for the rest of our derivation. The tool we need for this is called the Kronecker delta. It's a function that simply returns 1 if k prime is equal to k and 0 otherwise. If you can't see right away how this allows us to combine these derivatives together, just try a few examples on paper so you can see how it works. Since this lecture has been pretty long already, we are going to end things here and pick up where we left off in the next lecture. To summarize what we've done so far, we explained why we're talking about logistic regression with Softmax, even though this course is about neural networks. We know that the steps we have to perform to find the weight matrix W is to set up our objective function and find its gradient with respect to W and perform gradient descent. We separated this gradient into 3 distinct derivatives using the chain rule, and we just solved for the most difficult of these derivatives, which is the softmax. In the next lecture, we'll continue solving the other derivatives and combine them together to get our final gradient expression. Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python Part 1. Now that the hard part is done, we can go back to our expression for the gradient of the objective. We have these three derivatives which we need to find. Luckily, we already know the derivative for the softmax, and the other two are pretty easy. Again, work these out on paper if you can't see right away how these are derived, or consult your calculus textbook if you forgot which rules to apply. Although it should be pretty trivial. There are no steps between this slide and the previous slide. It's just a matter of applying the rules of calculus. The derivative of log of y is just 1 over y, and the derivative of w times x with respect to w is just x. The next step is to plug these in for our gradient expression and try to simplify. The first thing we can see quite easily is that y of nk prime appears both on the top and the bottom, so they cancel out. Unfortunately, we still have this pesky delta function, which ideally wouldn't show up. So the question is, can we get rid of it? Luckily, the answer is yes, but it requires a little bit of logic. First, remember that the delta function can only be 1 or 0. It's 1 if k prime is equal to k, and 0 if k prime is not equal to k. It helps to isolate the summation involving t and y, and to just forget about the sample index n for the time being. We can also separate the two terms in the summation into two separate summations. So let's look at the first term. Remember that delta is 1 only when k prime is equal to k. Therefore, for any other values of k prime, we get 0, and anything multiplied by 0 is still 0. Therefore, this is just equal to t of k. Next, let's look at the second term. Remember what I said earlier about dummy variables. Only dummy variables must exist inside the summation. Luckily, k prime is the dummy variable, and k is not. So in fact, y of k can be brought outside the summation. The next step is to realize that t represents a neural network target. Only one of the values is 1, and the rest are 0. Of course, in this scenario, it doesn't matter which one is 1, since we're just summing them together. And of course, 1 plus a bunch of zeros is still equal to 1. Therefore, this summation is just equal to y of k. Finally, we can plug this back into our gradient equation to get the following simple form. Now again, I want to remind you about this idea of dummy variables. As you can see, the variable n, which loops through the samples, is a dummy variable, and it exists only inside the summation. I and k, on the other hand, are not dummy variables, and they both exist inside and outside the summation. As mentioned earlier, they refer to the input node and the output node of our logistic regression model. The next step is to consider how this would be written in code. As a first try, you might do something like what you see here. First, we loop through all the input indices I equals 1 to d. Then we do a nested loop through all the output indices k equals 1 to big K. Then we do another nested loop through all the sample indices n equals 1 to big N. Of course, as we've learned before, this can be quite slow because Python for loops are slow. So the next question we want to consider is, how can we optimize this nested for loop so that we can avoid this slowness? Luckily, we learned this handy NumPy trick in my free NumPy prerequisites course. Whenever we see a sum over element-wise products, we remember that this is the same as doing a dot product or a matrix multiplication. If you recall, the NumPy dot function does exactly what we want. Using the dot function, we can make our expression for the logistic regression gradient much simpler. It's just x transpose times t minus y. Now, technically speaking, this is not a dot product, but rather a matrix multiply. You can use the rules of matrix algebra to do a sanity check and make sure this works. First, we know that the shape of W is d by k, and therefore the gradient should also be d by k. we know that X is of shape n by d. And we know that both the target and the predictions are n by k. So ultimately, we have a d by n matrix multiplied by an n by k matrix. As you know from your linear algebra studies, the inner dimension disappears, so the resulting matrix is of size d by k as expected.